Hello, this is Professor Kuehn. Welcome back to my lectures on astronomy, where we are looking at the work of Edwin Hubble, his book, The Realm of the Nebula. Selections from this text are included in A Student's Guide to the Grade Physics Texts, Volume 1, Chapter 26. The title of this chapter is called The Structure of the Universe. So far, what we've done is we've read the first few sections from this chapter together, where Hubble talks about the exploration of space, our knowledge of our own solar system, and then our knowledge of our broader galaxy, and then the distance between our galaxy and other galaxies. These are sometimes called nebulae because they appeared at first as faint wisps of color or light in space very far away until telescopes were strong enough to discern individual stars comprising them. So then what he does is he talks a little bit about the characteristics of the observable region. This is on page 324. He talks about how we know the distances to the various nebula, and remember the role that the Cepheid variables played in determining the distance to these nebula. And that brought us up to about 325, page 325. At this point, he's explained how we know that the nebula on average are about as bright as 80 million suns. So that's how bright the average nebula is. How do we know that the nebula are that bright? Well, it's from what we do is we measure how distant they are using Cepheid variable measurements. He went through this, explained this a little bit. So we know how distant at least some of the nebula are based on finding a Cepheid variable inside of them and measuring the distance to that Cepheid variable. And then we look at how bright that nebula that contains that Cepheid variable looks to us. And if we understand how brightness varies with distance, then we can figure out how far away that nebula is. And we find when doing this that the nebula are all about 80 million times as bright as our own sun, and the brightest ones are only about 10 times brighter than our own galaxy, brighter than the average. And the dimmest ones are only about 10 times dimmer than the average. So really the nebula are roughly the same intrinsic brightness. And once one does this, one can then conceptually divide space into shells of varying distance and count how many nebula lie in each shell. So this is explained at the bottom of page 325 in his section titled The Distribution of the Nebula. So he mentions that you can do something like this. You can imagine us sitting right here. So here's us. This might be our own galaxy. And then you can measure, you can conceptually divide space into a number of different shells. I'm just going to draw a few shells to give you a sense of this. So imagine sitting in our own galaxy and aiming a telescope at the sky and looking at how many nebula there are at various locations in the sky. And then each nebula, by its apparent brightness, you discern its location, its distance compared to us. So maybe you count several nebula out here at this distance, and then several of them in here at this distance. I'm just going to draw a few nebula to give you a sense of how this sort of measurement works. Okay, so you conceptually divide space into these shells, and you measure how many nebula there are in each shell. And when you do that, you find that there are about the same number of nebula in each volume of space. He mentions you can find that they are approximately uniformly distributed apart. He says they're about 500,000 light years apart. And from this, now he wants to give us a sense of kind of the density of matter in space. He says that there are about, and these numbers are humongous, okay, so just bear with him for a moment. He'll put it in a little bit more tangible terms in a moment, but he says the density is about 800 million solar masses per billion cubic light years. This is on the bottom of page 325. And then to put this in perspective, he says this corresponds to about 1 gram for every 10 to the 30th cubic centimeters of space. So if you're kind of counting up all these stars and all these galaxies in space, you can estimate the density of space, and it's 1 gram per 10 to the 30 cubic centimeters. And to put this in a little bit more tangible terms, he says that this is equivalent to 1 grain of sand in each volume of space that is equal to the volume of our own Earth. So in other words, the nebula, he says, are scattered very thinly. and space is almost empty. And he refers to this picture, this figure on 26.4, where he has a diagram, data showing the distribution of the spiral nebula from counts made by Dr. Hubble on photographs distributed at intervals over the whole northern sky. He says the horizontal line is the plane of our own galaxy, and the figure gives galactic longitude. It should be noted that spirals avoid the region of the galaxy, so you can't really see the spirals through our own galaxy, the edge of the galaxy, because we're kind of looking out through a bunch of matter and dust and other stars in our own galactic plane, so it's difficult to discern external nebula or galaxies far away from us if you're looking along the galactic plane. We should say right away that there's a couple of puzzles that this raises. So if you go back to page 326, he says, in this calculation, we consider only, and he's talking here about the calculation of the density of space, the density of matter we see in space. He says, in this calculation, we consider only the matter concentrated in nebulae. There is doubtless matter scattered between the nebula which has been ignored. How much, we do not know. We can only say that there is not sufficient to be detected, not enough to appreciably dim the most distant nebula that can be discerned. Now, opinions about this have changed a bit since the time of Hubble, and this brings us to an aside that he doesn't talk about here, but I might as well spend a couple of minutes talking about it, and this is the dark matter problem. So let me write this, the dark matter problem. And let me see if I can outline the problem. The essential point of the dark matter problem is that it seems like by counting the matter you see in the nebula and stars, which had formerly been seen as a good estimate of the mass of the matter filling space, it's now seen as a very poor estimate of the matter filling space. There must be an enormous amount of matter that we cannot detect. And it's not a small problem, it's a large problem. So here's the idea behind it. So I'll kind of lead you through the reasoning. So let's say, given Newton's law of gravity, that is, we know how matter attracts other matter. We know how the sun pulls on the earth. We know how the earth pulls on the moon. So given Newton's law of gravity, we can predict how groups of stars should cluster together and orbit around each other, you might say. You can use a computer that's running some code that simulates Newton's law of gravity, and you can make predictions. Given these stars, how should they be orbiting around each other? How should they be moving compared to each other? So for example, the stars in a spiral galaxy, like the ones that he was talking about, like M101 on the previous page. Okay, that's point one. Point two is that looking at these galaxies, like these spiral galaxies, the motion of the stars does not match our predictions. So looking at such galaxies, the motion and distribution of stars in the galaxies do not match our theoretical predictions based on Newton's law of gravity, and for that matter, based on Einstein's law of gravity. So there's a problem, there's a discrepancy between experimental observations and our best theories at this point. And here's the third point, is that the motion, the distribution and motion of the stars would match our theories if there was much more matter, there was a lot more matter, within each galaxy than what we can observe currently. And this isn't a small effect. This is where we need, so here's point 4, I'll make this into a separate point. We would need something like 85% more matter, or that is only 15% of the matter. We only can see 15% of the matter that would be necessary in order to account for the observed distribution and motion of the stars. So this is a big problem. This isn't like a tiny effect that we just need to tweak our theory to make it work. We're missing an enormous amount of matter. So the proposed solution is there must be some matter filling space, a huge amount of matter called dark matter. And so you'll hear scientists talking about the search for dark matter. They're doing that because of things don't seem to fit together. There's some major problems. And so it's interesting to note that this is not an unusual kind of approach in science. It's very common for there to be observations of nature and then a current theoretical understanding of nature. They don't match, and so scientists propose the existence of something that we don't see now in order to try to explain the effects that we see now. That's exactly why things like ether were proposed as a medium for carrying light. That's this kind of, the neutron was proposed by, I think it was Rutherford, to try to explain certain atomic properties. Enrico Fermi predicted certain particles that were later discovered in order to make theories match predictions. So this is a very common sort of approach. And it seems to be the most conservative approach in the sense that one wouldn't need to throw out your theories if there was just a lot more matter than we can see. Okay, so that's a quick introduction to the dark matter problem. And so now let's go on to the next section in Hubble's text that is called the velocity-distance relation. And in this section, he's going to talk about how we know, or why we think, that the distant galaxies are moving at very high speeds away from us.